Can you hear me okay? Turn it on. Oh, yeah, that would help. Hello. Okay. It's not working.
That's the arrow ones.
Oh, okay. Well, all right. Okay, well, thanks for inviting me. Thanks for the opportunity to get to share my work with everybody. This is work that I did at my previous postdoc at the Donostia International Physics Center in Spain. Now I'm at University of Tennessee as a postdoc working with Adrian Del Maestro. These are the references that I'm going to be talking about today. There's no machine learning in the talk, but at the very end, I'll give a couple suggestions for how to maybe extend it to include some machine learning type stuff. Okay, so the talk's about entanglement, so I should motivate just a little bit. What's interesting about studying entanglement, one aspect of it is that it can help to kind of fortify the bridge between lattice models that you can study on computers and field theories in the continuum that you study analytically. And so the classic example, I think, what's that?
So the video that looks on.
Tend to gravitationally attract computer problems. So this is all consistent. Okay, and maybe the clip works after that. So the classic example of this is a one-dimensional quantum critical system, where if you consider the entanglement entropy of some line segment, the entropy grows logarithmically in the size, and the coefficient of that is the central charge of the effective conformal field theory that describes the system, which is essentially counts the effective number of degrees of freedom in the system. And so you can do computer simulations, for instance, DMRG simulations on critical spin chains, and you can use that to easily read off what the central charge is of what the effective theory description of that system is. Another interesting aspect of it is it can be used to diagnose topological phases. So, for instance, in two-dimensional quantum systems with gapped topological phases, the entanglement entropy of some region A, the main contribution is proportional to the boundary of the region A, that's the area law. But there's a negative constant contribution that can be used to diagnose topological order. So, for instance, in microscopic models of the fractional quantum Hall physics, it can be used to diagnose the topological order in those systems. And you can't diagnose it in other means by looking at local order parameters, for instance. And I think it's interesting to point out that just this past year, the Dirac Medal was awarded to 4 researchers looking at fundamental properties of entanglement entropy. So, for instance, Cassini and Huerta showed certain fundamental properties of renormalization group flows and how those relate to entanglement entropy. And Ryu and Takenagi showed a prescription for calculating the entanglement entropy within the ADS CFT framework. So now moving on to how to calculate, I'm a numerical person, so how to calculate entanglement entropy in these lattice models. And I'm specifically going to be focused on quantum Monte Carlo methods for interacting fermion systems, auxiliary field QMC. So in this method, you simulate the partition function, trace e to the minus beta h, and then that can be decomposed into a discrete path integral in imaginary time, where these spins here are the Hubbard-Stratanovich fields that have been used to get rid of all the interactions in the model. So this is still a statistically exact formulation. And if you don't have a sign problem, then you can decompose this, the partition function, as a sum over positive weights. And you just need to use the Monte Carlo to sum over the field configurations, which I'm calling S. And then those weights can be easily written in terms of the Green's functions. The Green's function for a given field configuration is easy to compute because for a fixed Hubbard-Svirtanovich field configuration, it's a non-interacting model. So now how do you compute entanglement entropy in this framework? So I'm specifically going to be computing this second Renyi entanglement entropy, which involves the reduced density matrix squared associated with some region A that you want to compute the entropy for. And so Terra and Grover showed how to do this in this framework, which is to consider two independent replicas of the system with two independent Hubbard-Svirtanovich fields, S1 and S2. And all you need to do is take those Green's function matrices, restrict them to the spatial region A. So you form smaller matrices out of them. Then you multiply them together in this fashion to form what I'm going to call this Grover matrix. And then it's very simple to compute the second Renyi entropy. Now, all you have to do is to average the determinant of the Grover, this Grover matrix. And the average is taken over the Hubbard-Svirtanovich field configurations. So this is really elegant, and lots of people have used this to compute entanglement entropy and also introduced other methods. But the real limitation is that it suffers from rare events. So it's observable. It has a long tail distribution. So even on very small sizes and for moderate interaction strengths, there'll be, as a function of Monte Carlo time, there'll be moments where there's huge spikes. And then when you go to average all this data together, it's impossible to get a precise enough quantity to do things with. So now I'm going to introduce a new method to compute it, which is based on just considering that you need to consider two different distributions. So one is just this distribution Z0, which is the independent, the product of these two independent replicas. That's the distribution there. And now there's this ZA, which is the same thing, but now it contains this extra factor, which is this Grover factor here. And now having these two distributions, you can see that this average is just the same as saying I need to calculate the ratio of these two partition functions. That's this thing that I'm interested in, the second Renyi entropy. And so writing it in this way makes it clear that this is really like a free energy difference, the ratio of partition functions. And so now the name of the game is to take the fact that this is a free energy difference very literally, or as little as possible. And so what that means is to try to introduce some generalized ensemble that depends on some parameter lambda that is able to form a bridge between the Z0 ensemble and the ZA ensemble. And so it's hooked up in such a way that when lambda is 0, it gives you Z0. And when lambda is 1, it gives you ZA. And then now you can kind of continuously tune between these distributions. And then by doing so, there's a notion of work that can be done in that process. And so once you have it set up in that way, then you can use this fundamental result from Drzynski, which says that the average of the exponential of the work gives you exactly the free energy difference. In this case, it's the second Renyi entanglement entropy. So the only thing that's left is to introduce this generalized ensemble. And this is something that I introduced in terms of quantum spins originally, and then now translating it to fermion systems. So the idea is to express this generalized partition function as sort of like a grand canonical partition function. But instead of allowing summing over the particle numbers, you're going to sum over these subset entangling regions C, which are all possible subsets of the region A of interest. And there's going to be almost like some chemical potential, which will bias how many sites are populating this region, allowing me to tune from no sites within the region, all the way up to fully filling the region A itself. So I think the best way to illustrate it is by showing a little movie. So if I consider this would be like an 18 by 18 honeycomb lattice, and if I want to compute the entanglement entropy of this big region here, I start the simulation with lambda equals to 0. It's forcing no sites to populate this region. And then now I can perform a non-equilibrium simulation where now lambda is like controlling the chemical potential for sites to populate this entangling region. And lambda, or a black site, means it's in this fluctuating region C. And then for each configuration in here, it means that I'm including this extra weight factor. So now I'm tuning between the two distributions, and I can calculate the work that's done in that process. And so it's the calculations are incrementally manageable in that way. So now I want to get to kind of the results that came out of this. And so I'm happy to say that we were given the editor's suggestion for this, which I feel like I need to just brag about, because if I don't brag about it, then I'm sure nobody's going to brag about it. And also, I just wanted to show this cool little picture I made in Mathematica. So, yeah, getting to the model, we just choose the most basic model, the Hubbard model on the honeycomb lattice. I mean, this model has a long history. The whole phase diagram is known. And so it's known that at small u, it's a direct semi-metal. At larger u, it's an insulating antiferromagnetic insulator. And then there's a gross nouveau Yukawa critical point in between. So the whole point is basically to explore this phase diagram from the point of view of this entanglement entropy. And so the first check was basically to see that it gives the correct results. I'm comparing it with DMRG as a function of u. And the QMC data matches perfectly within the error bars. And so now we want to study kind of triangular regions with these sharp corners. And the whole point is that these corners will contribute a universal logarithmic term, which has never been, to my knowledge, calculated or observed in interacting fermion models. So this is really a first. And so we can see that for u equals 1, how much time? 2 minutes? Okay. For u equals 1, we can study both of these triangles. It looks pretty much like a line, but there's actually a small bend in this, which is a logarithmic term. You can subtract away the area law piece by doing a fit and reveal, and both of these things agree with the theoretical prediction for direct fermions at u equals 1. At the critical point, one of the triangles shows a larger contribution, indicating more gapless modes appearing at the critical point. And then for that triangle, we do a full sweep as a function of u, extracting the corner piece at all stages, and it's showing rough agreement with there being an extra bosonic mode present at the critical point, which is what is essentially expected. And for larger u, you can find a distinct contribution coming from the fact that there's Goldstone modes present in the mod insulator. So okay, the ML extensions may be another way of computing entanglement entropy for neural network quantum states, potentially. Also, optimizing these non-equilibrium protocols, you could put different chemical potentials on different sites and things. And finally, maybe looking at doing some image classification maybe on some of these fluctuating regions, and maybe using it to diagnose topological phases, things like that. So that's all I have. Thank you.
In the interest of time, yeah, let's
Okay.
end right now. Yeah.
Okay.
Thank you so much. Yeah. So let's head to the beach for a group photo and some fresh air. So we can come back at 4. So this.